But you may do this. Just let me make sure. Because don't you need chain rule there?
Uh-huh.
Good call. Hey, what's that derivative? Is it just e to the 2x?
Yeah.
No. Don't worry, you'll get used to this. That's common. It's a common error. And you go, wait, derivative e to the x is e to the x. Derivative e to the 2x. Remember what we had before? We said the derivative e to the u. Remember what we said you always did? We said it's always e to the u times the u prime because of chain rule. So what's derivative e to the 2x going to be? E to the 2x times a?
2.
And what's a good way to say that? 2e to the 2x. So hey, what would derivative e to 3x be? 3e to 3x. What's derivative e to 4x? 4e to 4x. These things help us, right? These things, I know I made a practice sheet with 23 problems. It's like I was this close to making 100 problems. And just give you 20 in a row where I said e to the 5x, e to the 6x. You get tired of it, right? But it would sink in. Good. Hey, so we got this. Chain rule, right?
Mm-hmm.
What's derivative? Cosine,
negative.
sine, or negative sign?
Negative.
Good, negative. But is that it?
No, times pi.
There's the g. There's that g. What's derivative pi x?
Pi.
Pi. Because derivative 2x is 2, derivative 3x is 3. What's derivative pi x? Just a
Pi.
pi. But I shouldn't leave it like that, should I? So I'm going to write that as negative pi. Is that okay, this? Now, where am I going to jam all this? All right, let's check it in here. You ready? There's e to the 2x. There's 2e to the 2x. There's cosine of pi x. Some of you do this. Some of you do this. That's okay. There's m. There's m prime. There's n. And lastly, what's m prime? M prime is negative, not a subtraction sign, but negative pi.
Professor, you got it
That's
wrong.
not right.
Which one did I miss?
Yeah.
It's wrong. The
Nah,
primes are wrong.
Oh, the m prime. Thank you so much. I did that on purpose. No.
M prime should go over there.
M prime is the what? 2, right? And what's this
Professor.
m prime right here?
Yeah.
You bet. So this is the 2e to the 2x. And let me squeeze that in right here. And thanks again. Everyone, here's m. And the m prime is at negative pi sine of
Pi x.
pi. I'll put this closer too. 2e to 2x. And that's a long expression, do you agree? But what value do we get to plug in here? It's not like we got to plug in x equal to 423.
0.
Right? We're only plugging in x equal to.
0.
We're going to evaluate that entire slope at x equal to 0. Well, is it coming so much in here? Is it 0? We'll see. Remember, look right here. You don't have plug cap. The sine of 0 is 0, but the cosine of 0 is.
1.
And what's e to the 0 again?
1.
1. All right, let's see what we get. E to the 0?
1.
See, we're going to evaluate all this stuff at x equal to 0. So before I fill in this answer, right here, y minus 1 equals m times x minus 0. Let me just do all this at x equal to 0. Okay? I'll put an equal sign. E to the 0, 1. I love this. I don't care if it's got a negative pi. What's the sign of 0?
0.
Plus?
Cosine of
Cosine of pi times 0 is cosine of 0 is?
1.
And lastly, what's 2 times e to the 0?
2.
So check out all that math, everyone. That's our slope. That's the slope of the tangent line. What do you all get? One times 0 plus 2 times 1? All right, let's get it in here. This problem is done. You may want to pretty that up though. Do you remember what I do with the normal line? All I do is, here it is. 2, I gotta
Flip it.
flip it and change sign. What's the 2 flipped over with a different sign?
Half, negative half.
There you go. Now you may be like, I want to pretty this up. You can. You might put it in the slope-intercept form. I think this is, here I'll just draw an error. Isn't that y equal to 2x plus 1? And that's y equal to negative 1/2 x plus 1.
Why'd you flip it again?
Perpendicular lines. Perpendicular lines have what we call opposite reciprocal slopes.
How do you know that's perpendicular?
Definition of a normal line. That's a tangent. That's a normal line. Cool. You can put it in your notes. Normal line is always perpendicular to the tangent line at the point of tangency. So a lot of times, look at the picture. Make a picture too. A lot of times in your picture, your normal line's cutting right through the what? Right through the curve, isn't it? Normal, it's important. When wait till you get to Calc 3, you find normal planes. And you find normal vectors. And these things are very helpful, especially with finding equational planes and stuff. So that idea of just normal vectors, really, really important in Calc 3. Right now, we're just talking about normal lines though. Cool. Yeah, wait till you get, you'll love vectors. Start doing vectors. It's like in this textbook, chapter 12. Chapter 12, you get into vectors, you'll love it. I'm not trying to be like, oh yeah, right. No, I'm serious. It just, it makes it really smooth, especially when you go 3-dimensional. Hey, great job with that one. Boy, a lot with chain rule. Any other weird chain rule problems? Now I'm going to you. Was there any problem from this sheet? Any problem I did in class? From last class or today? Or is there anyone in the textbook driving you crazy? You said, we want to work it before we jump into 3.5.
I have, but that's not.
Oh, you got one. Anybody else? Let me know. I'll put them on the board.
That's
If you
not-
saw one, it bugged you. Could be one I've already done. You go, can you do it again? Just change a number or something. Which one was it?
That's not chain rule. Let me see.
No, this is 3.4.
No, this is 3.1 actually. That is number
Oh, so it won't be chain rule. Let's do it then. And when he goes 3.1,
183.
remember in 3.1, all we knew was power rule. What number was it?
67.
All right. Shh, I love it. I love this problem. You know what it is on a piecewise? And they asked about, is it differentiable?
JVT, right?
Yeah, that's right. And when where's something not differentiable?
JVT.
JVCs. No jumps, no vertical tangents, no corners or cusps, right? True? It's got to be nice and smooth. Slope from the left must match the slope from the right, true? For something to be differentiable, and differentiable means has a derivative existing at that point, true? You can't have the roller coaster go like that. No, everyone's going to die. We're like, it's got to be nice and smooth. That slope from the left is going to match the slope from the right. Cool. All right, well, what do they got? And 3.1, number 67, page number
183.
183. All right, I got a piecewise. So and all you and I are going to do, they go, is it differentiable here? We're going to check the slope from the left, see if it equals the slope from the right. Period. X squared plus 1. You might make a sketch of this. Isn't that a problem? That's only if x is less than 1. And on the right, they got, that's if x is greater than or equal to 1. Is f differentiable? I'm just going to write DIFF, okay? At x equal to 1. The first thing I want you to check, everyone, before you do any derivatives, will you remember this? Would you make sure it's just continuous? If this thing's not connected at x equal to 1, game's over, it's not differentiable. Do you remember that? Thing's broken. How can it be differentiable? Everyone will die on that roller coaster, right? That's what we're saying. It's got to be connected first. Okay, but once it's connected, let's make sure that slope from the left is smooth with the slope from the right. True? Does that make sense? So first thing, let's make sure it's continuous. How do you do that? Plug a 1 in. Plug a 1 in. Make sure these numbers match here. Do they?
Yep.
Plug a 1 in here. What do you get? What's the y value?
2.
All right, 2. All right, plug a 1 in here. What do you get?
Same 2.
At 1 degree, it's connected.
Mm-hmm.
All right, so right now we do know it's continuous. I'm just going to make a note. Continuous, yes, at x equal to 1. True. See, they try to trick us there. They do that. And when they do that, they give you equal slope sometimes. But they're totally in different spots. Is it differentiable here? You're like, it's not even continuous. If it's not continuous, it's not differentiable. Cool. All right, so we did check that. Now is it differentiable? All right, so we're going to check. And when slope from left, and you know slope means derivative, true?
Mm-hmm.
All we're checking, does that equal slope from right? Period. Or you could say slope approaching from the right. You could say slope approaching from the left. You could speak like that, just like limits. Because slopes deal with limits. Remember the definition of derivative? Limit as h goes to 0, all that stuff, true? But this is an easy way to say it. So derivative from the left. Now that's from the left, that's from the right, true? Left of 1 and x from the right are 1. So everyone, can you help me out? What's the derivative of this from the left?
2.
2x, and what do I got to plug in here? So I'm going to drop a vertical line and say you need to plug in what value to x? X equal to 1. Really? Yeah, it's continuous here. And what's the slope from the right?
1.
Ooh, good. Everyone agree? mx plus b? Derivative of x plus 1 is just a what? 1. Is this number, when you plug in a 1 in there, equal to this number?
No.
Here's our math. This is going to answer our question. If they're equal, we're going to say yes. If they're not equal, we're going to say no. Is 2x, where you substitute 1 for the x, equal to just a 1?
No.
No. Sorry. That's 2. That's 1. What's the answer?
Not differentiable.
Not differentiable. You really? Yep. Sorry, you got some kind of what? You got a slope of a 2 going to a slope of 1, right? From the left, it's really steep. Then afterwards, it's a slope of 1. But see, that's a corner. It'd have to go slope 2, slope 2. Or slope 1, slope 1, right? And be smooth. Differentiable, smooth to the point. Does that make sense? Hey, that's good final exam 1, right? Right, there you go. Your little thing, you know, hey, is it differentiable here? I'd also ask, is it continuous?
So,
remember, Washington, D.C. is lovely.
yeah.
So if it's differentiable at a point, that means it has to be continuous at the
Okay.
point. Which means the limit has to exist at the point. Well, when it wasn't differentiable, do you agree?
Yep.
Well, let me hide this. Do you agree it was both continuous at x equal to 1, and that function had a limit existing at x equal to 1?
Exactly, yep.
Because if that's true, that has to be true. Washington, D.C. is lovely, but that was the only part that wasn't true here. Yeah? Any others? That was a good one. Everyone, I don't care. Today's Monday, right? If it's Thursday this week, and you hit me, and you're like, Emrys, can you do a problem from 3.1? I'll be glad to. Maybe you didn't get a chance. Maybe there's one problem that's bugging you. You want to work on it some more. It's still bugging you. If you've done every problem I put to the textbook, and you've exhausted it, I've got more. Right? I've got more practice. I'll probably hand these out at the end of class today. Just say if you want to practice some. The only thing is sometimes students get hooked on these because they're just little pieces of paper. They can work it with solutions. And I have the solutions posted in Canvas. But I always encourage, I would try all the textbook problems first, you know. You spend a lot of money on those textbooks. You might want to try those first and then try these. I stole half of these. Yeah, stole them. From like old, they release them. They're from AP exams. They release every free response section. Sometimes there's some good ones. I'm like, oh, that's a good one. I take it. And sometimes they'll release an entire year, like 2003, and get that practice problem down. All right, everyone in your notes? We are now finally going to do 3.5. You're probably tired of chain rule anyway, right? No worries, it's going to pop up every day, right? It really will. It will pop up every day. What's the derivative of y equal to e to the 2x? Is it just y equal to e to the 2x, y prime? No, but it's e to the 2x times a 2. But it was y equal to e to the x squared. The derivative would be e to the x squared times, what's the derivative of x squared? 2x. You see chain rule with the exponential? Okay, good. All right, here you go. Implicit differentiation. Everyone, implicit differentiation. It's the first thing, because you and I have covered all the derivative rules. So what's this for? Everyone, every problem I've done so far, I've been doing this. Do-do, 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 do-do. Every time I did you notice that? Or I didn't say y, I said f of x. F of x was explicit off that equal sign. Explicit. Explicit. This is titled implicit differentiation. So it sounds like with these problems, when you're not going to have that y just sitting what? Off to the left of the equal sign. You're going to get something like this. Like a circle. I thought we'd start with the circle. I think it's a good place to start when we're doing implicit differentiation. Okay? Oh, it's not y equals. That's not even a function, is it?